let's start with the next topic, robust surgery loading. So we also would like to hedge against uncertainty because we never know how long the final duration of the surgery will take. And therefore, we need some kind of robust formulation of this bin packing problem. Okay, so the task remains the same. We assign surgeries to operating rooms. And this time we consider only the offline cases. That means we know the surgeries in advance. This is because of our elective appointments for hip surgeries, knee surgery, whatever. Okay, but to account for potential emergencies, we still keep some capacity for these emergencies. So, for instance, we have an operating room of 8 hours. 80% is dedicated for elective surgeries, and 20% is used for emergency cases. Okay, and the same as before, nothing new. So we have still elective surgeries. So we have bins, which are our operating rooms. And we have a particular size and capacities of these operating rooms, and these are opening hours of the operating rooms. And now what is new is we can extend the bin capacity. So that would mean it's overtime, meaning that if a surgery would last for more than half an hour, that would mean overtime. Then we still would work on that. We would complete this surgery and then have some overtime. So we, in some sense, we can extend the capacity of our bin. Okay, and the next new thing is that we can schedule additional slack, unused times, basically, within the available capacity, okay, to reduce the probability of overtime and also cancellation. So because, as I said, we don't know exactly how long the surgery will last at the end, so we have an expectation time, but the actual time is not known. Okay, and to hedge against this uncertainty, we can also use additional slack, so unused time. Okay, other assumption is it's pretty common to have in hospitals, I mean, with Lauterbach that might change, but for now it's like that hospitals and each specialty has its own number of operating rooms for particular days. So oncology has the operating room for 5 hours on Monday and Tuesdays. Pediatric has operating room on Wednesday and Thursday for 6 hours, and so on. Okay, for this particular planning horizon, which is typically 1 week. And the problem is to assign the specialties to operating rooms and days. This is so-called master surgical scheduling problem, but we won't deal with that. So it's a question how much time to assign for which specialty. As I said, that might change in the future if we only will have some specialized hospitals. And then each specialty then schedules their surgeries into their assigned operating room days. Okay, so each ward, oncology or pediatric ward, they are responsible to schedule their own surgeries into their days and rooms. Okay, and then they plan some kind of slack, unused times for each operating room and day. Okay, and the objective is to minimize the probability of overtime. Okay. What is also assumed is that surgery durations are normally distributed. That could be seen critically, but if you apply the central limit theory, then you know if the hospital runs forever, then we would have these normally distributed durations, which could be a valid assumption. Okay, but we will see in a minute if this is a valid assumption or not. Okay, the notation is as follows. We have sets, so we have, let me choose the laser. So we have a time plan horizon, so the set of days, the set of operating rooms, K, set of specialties, oncology, pediatric, cardiology ward, and so on. KST is the set of operating rooms assigned to specialty S on day T, and NS is the set of surgeries to be planned for specialty S. Okay, then we have parameters, the capacity, C, the mean duration, what we would expect, how long the duration at the surgery I will take place. The standard deviation sigma for surgery I, and beta, this is a parameter which influences the probability that surgeries end on time so that we won't have overtime. Okay, we will come to this parameter in a moment. And the variable, so this is the output of the model, is what we would like to see. So these are the results. This is the capital N is the set of surgeries which are assigned to a specialty S in operating room K on day T. Okay, so we know how many surgeries the oncology can do in operating room B on Wednesday. Okay, and then the respective overtime, O for specialty S, operating room K and day T. Okay, so how to determine the slack, the planned slack, and how to also to account for the capacity constraint. So the planned slack time depends only on the variance, okay, of the duration and not the expected mean value, because it doesn't matter if we expect a 2-hour duration or 3-hour duration. What we are interested is in the variance, and it's often like that if the duration is anyway pretty long, so it's a rather complicated surgery, then the variance will be also higher than for short surgeries that may be some kind of common ones. And often this variance or the standard deviation is also smaller for these cases. Okay, so the expected duration of all planned surgeries is the sum of expected durations over all surgeries of specialty S in operating room K on day T. And the same for the variance. Okay, so sigma squared is the sum over all surgeries I. And then the planned slack, so the unused times, is delta, and this is the product of beta multiplied by the sum of these variations of the variances. Okay, and because it's squared, we can simply say this is this planned slack is beta times the standard deviation for surgery of specialty S in room K on day T. Okay. And the capacity constraint we have to follow is that our expected duration plus the planned slack time, so the planned unused time, shouldn't exceed the capacity of operating room K on day T plus the overtime we have to take into account. Okay, so this has to be fulfilled, this constraint. And some words about beta. So as I said before, this is a parameter that determines the probability that surgeries will complete on time, so will be punctual, and we won't have overtime. And every time when something is difficult to determine, as a modeler, we say, okay, the decision maker has to take this and to define beta, which is always the question how to find a good value for beta. Okay. That's not that easy, because a higher value of beta will lead to, for instance, lower operating room utilization, so more slack and less surgeries are planned. Why is this? If we look back, we see here that the planned slack, so the unused time, is a product of beta times the standard deviation. Okay, the higher beta, the more slack is planned, and therefore we have less surgeries that we can plan, okay, of course less overtime, and on the other hand we can assume that we could have higher quality of labor and care because staff is not under stress and can complete the surgery on time. Okay, so let's have an example. So if the decision maker, if the management says, okay, beta should be half, meaning that half of the time we assume that we need more time than expected and half of the time less time. Okay. Okay, with that, we can also assume that our surgeries are normally distributed with the expectation of mu and standard deviation of sigma. And then we now have to understand the probability of overtime. Okay, so if we assign this surgery to this operating room K on day T, what is the probability that we would have overtime? Okay, so that the staff has to work longer than expected. So we want to know that M, the duration of our surgery, exceeds the expected mean value plus this slack time, the unused time. Okay, so we can simply replace delta by beta times standard deviation from the previous slide, and then simply neglect the indices, okay, for simplicity. And then we can see here that if we assign the right-hand side, sigma, mu, and sigma to the left side, then this might be familiar to you. This is this kind of normalization, okay, in order to use the standard normal distribution table. Okay, but if you look in this table, then you see that you find only values for smaller than or equal than beta, okay, and not larger than. Therefore, you need simply the counter probability, so 1 minus the probability that this is smaller or equal to beta, and then you simply can use the cumulative distribution function of the normal distribution. Okay, so because we know beta is 0.5, if we look up this in the table, then you will see that in 69.15% of the cases we will finish our surgeries on time. Okay, and with the counter probability 1 minus, so roughly 30%, is that we need some overtime. Okay, so this is the probability of working overtime, and this one is the probability of completing the surgery on time. Okay. Okay. So, phi, as said before, this is the cumulative distribution function, and you simply can use the table, okay, to look up this number here. Or the other way around, if you would like to determine beta, you can also go backwards. Okay, if you know you would like to be on time in 20% of the cases, then simply backward putting in and check the table for that. Okay, so you could have different objectives. The first of all is to minimize the total amount of overtime, because we don't want to work more than necessary. So we simply sum up the overtime over all specialties, operating rooms, and days. Okay, but that only to minimize the total amount of overtime might be not very beneficial. Do you know why? Do you have an idea why it's not the optimal? Why should we also use additional maybe objective functions or alternative ones? Okay. Why not simply going for reducing overtime? Well, what could be the reason? Isn't that great if we minimize the overtime so we don't have to work more than necessary? Mm-hmm. Sorry? Exactly. Exactly. So if we would like to avoid overtime, that would mean that we open new days, open in some sense, so the patient has to wait longer. Exactly. So this is why we also would like to maximize the total number of free operating days. So sum up all surgeries that are not assigned to specialty S, so overall S, operating room K, and day T. So instead of assigning one specialty to, let's say, 3 days, then rather block several rooms for this specialty at the same day, okay? So not distributing on Monday, Tuesday, Wednesday, but rather block all 3 operating rooms on Monday, okay? So to keep the other days off, okay? So we in some sense, we would like to cluster the surgeries. and also minimize the total amount of unused capacity. This is taking the maximum of, if this would be negative, that means if the expected duration plus the unused time, so the slack time, would be larger than the capacity, you would have here a minus. Okay. Otherwise, if you have positive value, that means you have unused capacity, C left, and we would like to maximize that. And why do you think is this useful? Why having unused capacity could be beneficial? Okay. So we are always talking maximize utilization because otherwise you have idle times and so on. Why could that be beneficial? To keep some of the capacity unused. Some ideas? Why not putting every surgery to 1 day, 1 operating room to 100% and that's it, yeah? Exactly. Exactly, so one point is that it takes longer than expected, exactly. What could be the other way? So if we pack everything in to 100%, we have no capacity left. We are currently in this robust planning. What does it mean? Mm-hmm. Exactly. Yeah. Exactly. So that is simply to also hedge against uncertainty in the sense that emergency can come in and we can use this unused capacity for this unknown and unforeseen emergency cases. And as always, if you have several objectives, so you have a multi-objective problem, there are several approaches how to deal with different and might be conflicting objectives like this. Here we have a minimization, here we have maximization, here overtime, here days, here capacity. So the question is how to deal with this multi-objective problem. And what they've done is to use the lexicographic optimization, meaning that they want to minimize the first criteria, the amount of overtime, and if the resulting decision variables are the same, so we have multiple solutions for this, then we compare that with the second objective function and then choose the one who maybe maximize the total number of operating room days and so on. Okay, so this is one way of dealing with multi-objective problems. Okay, so of course, as always, in general, there are NP hard. That means we cannot simply use Gurobi or Cplex or something like that, but we need some kind of heuristics. And the basic heuristic, which, by the way, is still used by hospitals also nowadays, is the first fit dispatching. So we remember the first decreasing heuristic. It's very, very similar, but here it's called first fit dispatching. Okay, so you have your operating room and you compute your slack times, and then as soon as you cannot assign a surgery to this operating room anymore, then simply open a new one. So this is basically nothing new. You know it from the also from the transportation problem. Okay, but of course there exist also sophisticated and improvement heuristic that can also improve the first fit dispatching heuristic. Okay, in this lecture we will consider the longest expected processing time first, so LPT rule and the sampling procedures. Okay, and then we simply compare that with the first fit dispatching rule. Okay, so the basic heuristic that, as I said, is still used in hospitals. So first of all, we assume that we have a long waiting list and the demand is always greater than our capacity, which is not unrealistic, especially I told you in UK and Malta. The waiting lists are so long for standard surgeries like hip or knee surgeries that sometimes they even go and come to Germany to get this done because they will have to wait for years for these standard ones, or at least months. Okay, so this is not a crucial assumption. Then the FFD rule assigns the surgery from the top of the waiting list into the next open OR in which it fits. What does it mean? When does it fit? It fits if the expected duration plus the slack time is below the capacity of operating room K on day T. Okay. So we don't consider overtime for now, for this heuristic, which makes it easier to compute. Okay, and as soon as all surgeries are assigned, then we are done with this heuristic. Okay, and how to determine the slack for this first fit dispatching heuristic? In contrast to the first equation I've shown you, here we use less statistical information, so let's compare that. Before we had the planned slack was determined by beta times the sigma. Okay, show you the original one. Okay, here's the one. So here we see that beta is multiplied by the standard by the variance of the surgery I, and the surgery I depends on the specialty, the operating room and day. And here we neglect that, and what we are assuming is that, so what we assume is that the standard deviation sigma is the same for all surgeries for this particular specialty. So all oncology surgeries have a standard deviation of 30 minutes, for instance. So this is again easier to compute because the standard deviation does only depend on the specialty anymore and not on the room and the day. So therefore we can simply take the standard deviation out of the square root and multiply it by the number of surgeries, okay, of this specialty for this operating room on this day. Okay, so an example maybe. We have again a beta of 0.5, a capacity which is available for 420 minutes, so 7 hours, so we have an operating day. And all the surgeries have a standard deviation of 15 minutes. Okay, then we have the waiting list. So the first patient has expected surgery duration of 60 minutes, the second of 80 minutes, and so on and so on. Okay, and now we have to assign that to the operating room day, considering that every surgery deviates plus minus 15 minutes. Okay, and the question is, which patients can be assigned to the first available operating room day? We remember this is how the slack is computed. Beta times the number of surgeries times the standard deviation, which is 15 minutes every time. And here you see beta is 0.5. We have only one surgery. The first patient is assigned, and the standard deviation is 15 minutes. Okay, that means the total occupation time is 60 minutes of expected duration plus this unused time, the slack time, and we have to account for 67 minutes and a half, okay, for the first patient. The second patient, so the only thing that changes is the number of surgeries. So we have 2. Okay, so the total occupation time of this room is 60 for the first patient, 80 for the second patient, taking from this one, plus the slack time for both surgeries. And you can see here, the higher the number of surgeries, the more slack time we have to take into account. And then we sum up the occupation time, and the fifth patient ends after 366 minutes and 77. Okay, so that means the last patient who requires 70 minutes, he cannot be assigned to this operating day anymore. So therefore, because we try to avoid overtime, we assign the sixth patient to the next day. Okay. So here you see the first till fifth patient will be assigned to the operating day, and the sixth one is scheduled to the next operating day. So the problem is here that we still have 50 minutes left Okay, we have unused capacity of 50 minutes. Okay. So the question is it really optimal or not to assign the 6th patient to another operating room a day, sorry. Okay, although we still have 50 minutes left. So if we would assign him, then we would know that 20 minutes we have to work overtime. Okay, if we would allow overtime. Okay, so let's try another heuristic. What about if you use the longest processing times first? So the task remains basically the same. We schedule the same surgeries as the basic heuristic, and we also must plan the surgeries for the same specialty, but we can use other operating room days. So the surgeries remain the same within their assigned specialties, but they can be assigned to other days. Okay, so compared to the FFD solution, we might choose other days on which the surgeries are scheduled. So this is the last point here. Okay, so the specialty stays the same as in the FFD, but we might change the operating room days. Okay, and for every specialty, we have a set of surgeries, and they have to be planned in, which is the union of surgeries over all operating room case and days T. Okay. So what is the LPT rule? So what the main idea is we try to assign the longest surgeries first, okay? Because long surgeries often have also the highest variances. Okay, so for this ideas, we first of all have to sort the surgeries again in non-decreasing order, so that we have the longest durations first, and then we assign each surgery to the operating room that doesn't exceed our capacity. Okay, as before, we neglect overtime. Okay, but this time we determine the planned slack delta as before. So we use again more information than in the basic heuristic. Okay, so we use the same equation as before, the original one, where all the standard deviations depend on the surgeries. Okay. Again, an example, so we have beta 0.5. Now we still have the available capacity of 420 minutes, but we have different variances. Okay, so 170 minutes for the first patient, 330 for the next one, and so on. And the same question arises, so which patient to assign to which operating room day. Okay, so you can see here the sorting was already done. So the 4th patient requires 120 minute duration, and this is the longest one. So this patient should be assigned first, and so on. So the 5th patient requires the shortest duration for the surgery. Okay, and then the same procedure as before, but we use the original formula. So we need beta times with a variance of 390 minutes and assign it to the 120 expectation time. Okay, so this is basically the same. So we go through the entire list, and we can see here after the 3rd patient, we are here done with 397 minutes. So is it the better solution? What do you think than before? Because we still, as before, we still assign 5 patients to this operating day, and the 6th patient we assign to another operating day. Okay. But compared to the FFD rule, the basic heuristic, is it the better one? We couldn't assign more patients. So that is similar to the basic heuristic. But what would you say? Is that a better one? Or even worse one? The same? Doesn't matter? What do you think? So we had, just a reminder, we had 420 minutes in total. Okay, and we stop after reaching 397 minutes. Yeah? you're absolutely right. So it's not that easy to say if this is really better, because yes, we have less unused capacity, because now we only left with 20 minutes. So we utilized our capacity better. But on the other hand, what about if emergencies are coming in? We have less capacity free for them, okay, to put them or assign them into this operating room. So exactly, so that is not always easy to answer this question, what is really better? Okay, you always need some kind of objective function that you follow. And in this sense, if you would like to minimize idle time, whatever, then that would be a better solution. If you would like to minimize or maximize the free operating days, that doesn't matter. It's the same as the basic heuristic. Okay, so you always have to question yourself, what kind of objective would you like to achieve? Okay, so another heuristic is sampling procedures, where you differentiate between scenarios. So in contrast to this longest process first, we consider now different scenarios for the samplings with different degrees of freedom. So what does it mean? So the first scenario is if so surgeries must be planned on the same day to which they were assigned in the basic solution based on FFD. Okay, within their operating room days of their specialty. So if a surgery for cardiology or whatever was initially planned for Monday, it must remain on Monday within the cardiology operating room days. Okay. The second scenario is surgery must be planned on the same day to which they were assigned, okay, to all specialties supported by the same unit. So switch a bit if we stay in the same unit, okay, so same operating room team, because sometimes if you change the surgeries, you also have to change the entire team, because you need some other specialist for this particular surgery, okay. So a cardiology surgery, again scheduled for Monday, can remain on Monday, but can be within their operating rooms assigned to cardiology or any other specialty, okay, managed by the same team. The third one, surgeries must be planned on the same day to which they were assigned to the basic solution. So we leave the specialty here, okay, so the specific operating days for specialties are not considered anymore, okay. So the key constraint is still maintain the same day. Okay, then fourth scenario, surgeries must be planned on the operating room days assigned to their specialty. Okay, so this scenario was also used for LPT. Okay, so a cardiology surgery can be on any cardiology operating room day. So they are not restricted to the original day. Not on Monday, they can also use Tuesday or whatever. The fifth scenario, surgeries must be planned on the operating room days to all specialties. Okay, so it's similar. This is basically the combination of all. A surgery can be scheduled on any operating room day, okay, to any specialty with the same operating room team. And scenario 6, a surgery may be planned on any operating room day. So this is no restriction at all, okay. Then this scenario gives us the maximum flexibility. Okay. And the assumption is more degrees of freedom should lead to more freed capacity. Let's see if this is true for computational results then. So, but this is the assumption we have to make. Okay, so what is the general procedure? Sort surgeries first in non-increasing order. Okay, this is the same as LPT. Then at each iteration, we take Z surgeries from the top of the list and consider if we would like to dispatch them or not. And at each iteration, do the following. Okay, if the operating rooms fits without generating overtime, then use it by scheduling priorities. Okay, if there is no operating room available, so only operating rooms are available where we need overtime, then use the one with the smallest possible, okay, overtime, and then determine the drawing probability, PI. So the probability that we choose surgery I to dispatch it. Okay, if they're all done, then that's it. To all surgery we assign some kind of drawing probability, and then we run some kind of randomized sampling procedures to see which surgery to take first. Okay, so basically we assign higher probabilities to those surgeries which should come first, with the highest priorities B. And the question remains how to determine the priorities, how to determine the probabilities, right? Okay, so let's have an illustration example to see. So with Z2, we would, in each iteration, we would like to choose 2 surgeries. This is Z. In the first iteration, we sort, first of all, in a non-decreasing order. Okay, so this is already done. And now we would like to choose the first one and to compare both, okay, by calculating the priorities for the first and for the second surgeries. Okay, and based on the priorities, we determine the drawing probabilities. Okay, and let's assume, so we have to draw either surgery 1 or 2. Okay, so assume that we have chosen surgery 2 to draw and to schedule, so delete it from the list, and then again in the next iteration we choose and compare again 2 surgeries, because that is 2. Okay, and the same starts again. We calculate the priorities, drawing probabilities, and so on. Okay, so as I said, so first of all, how to determine the priorities, but also at the end then the drawing probabilities. Let's start with the priorities. Okay, so the idea is to assign surgeries so that the slack time is minimized. Okay, so we don't want to have too much unused time. Okay, so to determine the priorities, we first of all need some kind of definition. So first of all, if the operating room is empty, then the slack time is computed by beta times standard deviation of the surgery. If this operating room is already filled, then we can compute the additional planned slack. Okay, this is simply delta, so this is the additional, so all the slack times of the previously assigned surgeries minus and plus the current one minus the previously assigned and planned slack times. Okay, so this is the additional slack time if we would assign the surgery I to an operating room that is already filled. Okay. So this simply increase in slack time if surgery I is planned in a filled operating room. And then we define the profit, okay, of planning the surgery I into a filled one instead of an empty one. Okay, and this is called omega. So it's simply the difference between assigning a surgery I to an empty room, okay, beta minus sigma, minus the delta, so the increase in slack time. Okay, and as soon as the omega is positive, as soon as we have positive profit, meaning that we have here the additional planned slack is smaller than putting it into an empty one, as soon as this is positive, we know that we gain some kind of profit. Okay. And why do we call it risk pooling? What do you think? Why is it beneficial to assign a surgery to already filled one, a filled packed operating room instead of an empty one? It's because of risk pooling effect. But what does it mean? What do you think? Why do we pool risks? Maybe the first question of what is risk here, right? What could be the idea behind it? Why do we call it risk pooling? And it could be beneficial. Yeah. Exactly. This is the absolute perfect answer. And this is why we call this risk pooling, because some surgeries take less, takes longer, and then they could cancel out. Okay, and this is why it could be beneficial to have that. Okay, so this is first of all the profit, and based on these definitions, we can now define the priority V, which is the maximum omega, so the maximum profit we could gain if we assign surgery I to an already filled operating room. Okay, and the task is to minimize the planned slack by clustering surgeries with a similar variability on the same operating day. So before that it was about operating rooms, and now we would like to minimize the slack by clustering similar surgeries together, because you can see here an example. So let's consider two surgeries. Both take 100 minutes of operation time. The first one has a standard deviation of 10 minutes, so 100 minutes this is the expectation time plus minus 10 minutes. And the second surgery has a plus minus of 15 minutes. So if we assign similar to the same, the first example is if we assign the surgery with different deviations, okay, with standard deviation. Okay, here, so the one with 10 minutes of standard deviation and the second with 50, and the same on the second day. Okay, comparing that with if we put the similar surgeries to the same operating room day. Okay, if we compute now the slack time, okay, this would be 51 beta for the first day and 51 beta for the second, and overall we have 102. Okay, if we assign similar surgeries to the same day, then we have a higher slack time here, but less here, so that overall we have less slack time, less unused time for the second case when we put similar surgeries together than mixing them. Okay, so better to cluster same variabilities to one day in order to reduce slack times. So this is the idea. Okay, so we choose this one. Okay, so the next question is how to determine the drawing probabilities. Now we have the priorities, and now we would like to say with what kind of probabilities we choose surgery I to this particular day. Okay, so how to determine that? We start with the regret. Basically, how much I would regret if I would choose option A instead of B if I know if it turns out that B would be better. Same for the surgeries. What if I choose surgery I, but should actually choose J? So the higher the difference, the higher this regret of choosing the wrong surgery to assign that. Okay, and drawing probability is then defined by the product of C, some kind of constant, I explained that then, multiplied by 1 plus this regret to the power of alpha, and alpha is a bias factor, so the higher alpha, the more I penalize the regret. Okay, and C is simply a normalization constant, because I would like to have probabilities between 0 and 1 so that they sum up to 1 at the end. Okay, this is simply C here. Okay, but the interesting part is how to choose alpha, so how heavy I would like to penalize the regret. Okay, so let's have a look at an example. We have an alpha of 10, okay, and a Z, so I will choose always 9 patients from our list. Okay, and the computational results are as follows. So first of all, we have some kind of sampling procedures, and the last one is the regret-based random sampling. The base solution is what the hospital has used, and LPT is the longest processing times first. Okay, so if we consider that based on a 1 year data, we can see here the average overtime. So this is actually pretty good, and maybe except of the LPT. the number of free days. If we use the base solution, then we don't have any free days available anymore, so everything is packed. Here we have the average free capacity, so you can see here it's not that much in comparison to the, let's say, random sampling, regret-based sampling. And of course, the better the heuristic, the more computational time you have to take into account. So more expensive is to determine the solution. Okay, but it leads the highest number of free days and the highest number of free capacity that could be at the end used for emergencies. Okay. Questions? Okay. So, and here, maybe a side note, we don't use improvement heuristics because they had simply not a real impact on the results. And you can see here that it's all, you can see here that the improvement is really small, right, already. Okay. And then another one to compare it with random sampling. So just briefly, nothing that is really surprising. The more freedom you have, the better the results. The more free days you have, the more free capacity you have. Okay, so the scenario 6 was the one with the most flexibility. We are not restricted by specialty, so that we can use the capacity much better. Okay. So nothing surprisingly, and for every scenario, also for the base one, we don't have overtime, so that would even work in practice. Okay, so this is maybe a good result. Okay, so as I said, nothing new, but some critique about this. The heuristics, of course, yield better capacity utilization than the base one, or let's say the solution that is used in practice. But we have no information about the possible still existing improvement potential, because we know heuristics will give you a good solution, but you never know how far you are from the optimal solution. You can be stuck in a local optimum, but you don't know where the global optima is. Okay. And it doesn't consider different changeover times, because it's like in a production site where you have to change the products from, I don't know, from chocolate ice to vanilla ice. If you would like to change it, you have to clean the entire equipment. Okay, so it might be better in factory production side that you produce several packages and lots of chocolate ice first, then clean it once, and then start with the production of vanilla ice. This is pretty similar here. If you change the surgeries, you need to adjust the equipment, you need different stuff, you need to might have to use and adjust the bed, the equipment, the electric devices, and so on and so on. So that could take some time, and this is not accounted in here. And what is also pretty critical, that we assume normally distribution durations times of the surgeries. In a practical seminar, they checked historical values and data, and they found out that actually it's not normally distributed, but rather log normally distributed. And what they've done is that they extended the robust surgery loading model by using this log normal surgery distributions, and then they approximated the solutions and implemented heuristics. And you can see here, so on the x-axis, it shows the load increase. This is the normal load increase, okay? And then if you increase the load, the number of surgeries plus 10%, 20, and 30%. And you can see here that the green line is the overtime. It doesn't change that dramatically till one point, and then it's has increased significantly. Okay. On the other hand, the blue one is the number of operating rooms we could save, and you can see here it's also that it decreases. Sorry. Okay, so the main message was that it is not normally distributed, So the assumption is not really realistic, but rather log normally distributed. So if you open a paper and you have for your master thesis or for project or whatever, or even if you go to a factory, to a hospital, whatever, and you would like to use some kind of research result, check always the assumption before you can use it, okay? If these are realistic or if you have to adjust that. Okay, questions so far? Okay. Then I would finish with the last point, sequence in elective surgeries. So we are going from the tactical planning to the operational one, meaning that till now we assign surgeries to bins, operating rooms, operating days, and now what we have to do now is to sequence the surgeries. Okay, so the assumption is that the week assignment was already was done. Okay, so we know how many surgeries we have on Monday, Tuesday, and so on. And now we would like to decide if Peter is first, and then Maria, and then so on and so on. Okay, so we have to sequence the surgeries. Okay, elective surgeries belong to the same operating room. They have to be scheduled. Okay, and we could consider different objectives. Again, we could minimize delays, idle times, overtime. So this has been done in literature already. But the new thing and the new idea was to minimize waiting times for urgent surgeries. Okay, what about that? Okay, what kind of results do we get if we would like to minimize the waiting times of our emergencies? Okay, but the factors that influence our sequencing decisions is, of course, the variability of the duration of surgeries. Okay, we never know if this is really how it will end. We don't know the actual operating times. We need some kind of pre-operative examination, some kind of MRT scans or whatever. Then, of course, at the same time, simultaneously, we need different resources: surgeon, anesthetist, operating room itself, but also equipment and nurses. Okay, and not only the pre-surgery examination, but also the post-surgery assignments. We need some kind of, again, anesthetist, but also recovery rooms for the patient to wake up. So this has also to be taken into account. Okay. Okay, and we have to implicitly consider emergencies. Okay, so one idea was to adapt that from manufacturing processes to see patients as jobs, okay, and which job to assign to which machine. So we have 3 patients here, A, B, and C. That means how many possibilities do we have to schedule them? So we could use the sequence A, B, C. A is first, then B, then C. How many in total do we have of possibilities to sequence them? If A, B, C is the first one? Yeah. Exactly. So simply 3 faculty. So we have 6 possibilities. Exactly. Okay. And now, why can we... so the example is, let's see the combination and start with B, then C, and A. Okay, B starts at, let's say, at 8 a.m. and requires 3 hours. Okay, so end of surgery is 3. He can instantly start with a recovery. Okay, it takes 1 hour for the patient to recover, for patient B. And C is now starting at 3.5. Why? The surgery of B ends at 3. Why not starting with C instantly? The operating room is open, right? It's free. B has left the operating room. Yeah, maybe someone else. Okay, B has left the surgery room, is now in the recovery room. Why not starting at 3? Why leaving half an hour? It's, maybe something that you can see which room is occupied. Yeah, which room? The surgery room is open. It's free. But which room is not free? At 3. The recovery room, exactly. So that means even if we would start at 3 with patient C, and the patient requires only half an hour surgery, then the patient has to go to the recovery room, but it's blocked. So if we would start at 3, at 3:50 we are done, but then the patient has to wait in the surgery room to wait for the recovery. Okay, so this is why we don't start with C at 3, but at 3:50, at 3:05, because at 4 the patient is done and can instantly go to the recovery room. Okay, so 3 plus 1, it's 4, and C has to wait half an hour for the surgery, okay, because B blocks the recovery room. Okay. Similarly, okay, we finish with C at 4, but we wait till 5 because the recovery room is blocked till 6. Okay, so A has to wait for 1 hour. Okay, so here we see all the combinations, all the 6 combinations, ABC, ACB, and so on, and you can see the end of the operating room occupancy and also the end of the recovery room occupancy. And you can see here how long the patients have to wait. So C has to wait half an hour, B, and so on. Also the same here, C and F, C and A have to wait. And here A has to wait 1.5 hours. And you can see here the best solution is for the CBA, because after 4 and 5 the surgery room is open, after 5 also the recovery room is free. Okay. In all of the other cases you need to wait longer. Okay, so this is the optimal solution for our cases. No, we have no waiting times and minimal research usage. Okay. So the problem is still that we don't consider possible emergencies or duration variability. And this is why we now check the break-in moment optimization, BIM, okay, because we would like to also account for emergency surgeries. Okay, and the question is how to minimize the waiting times for these emergency surgeries. We could reserve an entire operating room for emergencies, so keeping always a room open for emergencies. The problem is that they can be open and we have a long waiting list for electives. So someone is, maybe the status is not life-threatening, but the patient is in pain, so could be do some kind of surgery, but because we block one entire room for emergency, the patient has to wait. So this cannot be optimal. And also, if we have an emergency and shortly after that we receive another emergency, then the operation room is still blocked. So the next one has still to wait. So that cannot be efficient, and also it's pretty expensive to keep one room open for emergency. So the second alternative is to use operating rooms but keep some capacity for emergencies. Okay. The problem is that yes, we have to cancel or reschedule elective surgeries. Okay, and even if we have capacity available, maybe at the end of the day, it could happen that the emergency patient has to wait because we cannot interrupt an ongoing surgery. Okay, never stop a running system, right? Okay, so therefore we focus on the second alternative. Okay, and we need some kind of definitions. So first of all, we assume that all operating rooms can be scheduled without breaks, so one after another, and the slack is always planned at the end of the day. Okay, so 80% of the operating room capacity is used for electives, and then at the end 20% for emergencies. Okay, so capital J is the set of available operating rooms, as J denotes the moment when the operating room surgery starts in operating room J. E is the completion time, so the final time when the surgery is done in operating room J. And the latest start is S, and the earliest endpoint is E. And between S and E, this is the occupied time. I maybe should give an example. I don't know if this necessary. So you have the operating room 1, and it starts at 8 EM. Then you have the second operating room. It starts at 8:30, and the third one at 9 EM. Okay, so this would be S1, S2, S3, and as the capital S would be done this 9 EM. Okay, so the latest one. Okay, and the finishing time is the same. Okay, so in between we have surgeries. Okay, and we finish here at 4 p.m., 4:30, and 5 p.m. Okay, p.m. Okay, and the last one, the earliest finishing time would be here. Okay, that would be the last one, so 4 p.m. And in between 9 and 4 p.m., all operating rooms are busy, okay, and occupied. So this is the idea. This is the occupied interval, okay, so between this one and that one, okay, this is our occupied interval, okay, where all operating rooms are busy. And now we have to determine the break-in moments, where we can, if an emergency comes in, we can assign that. Okay, so in this case we would finish here, so that could be a break-in point, that could be a break-in point, that one, but also before that one, before this one, before this one, and also at the end, obviously. Okay, and the interval between two break-in points is called break-in interval. Okay, we have here some kind of example. The question now is to reduce the waiting times for emergency. The idea is to evenly distribute all the elective surgeries evenly. Okay, so that all these intervals, this break-in interval, should have same length. Okay, so if we would start both surgeries at 8, okay, and both requires, let's say, 3 hours, both finishes at 11, and an emergency comes in at 8:10, then the patient has to wait for almost 3 hours. That cannot be optimal, and this is why we try to evenly distribute that, so that we have often to mix it, so that we have often break-in point where we can assign the emergency. Okay. So here you can see this is the occupied interval I've just explained. So this is the starting point at 8, and this is the earliest surgery that finishes. Okay, and here we have the intervals between the break-in moments. So we could assign that at the beginning, after surgery 1, after surgery 4, after surgery 2, and so on. And time in between, these are the break-in intervals. And you can see here they are not evenly distributed. So the idea is how to assign the surgeries so that it's more evenly distributed. Okay, so that we can assign an emergency patient every whatever half an hour or something like that. This so that they don't have to wait that long. Okay, so this is unevenly. And now an example for evenly distribute the break-in points in moments. Okay. And if you do it like this, you can see here every, let's say, 15 minutes, a surgery ends either in operating room 1 or operating room 2. And every 15 minutes you can, if a surgery comes in, you can assign them into these break-in moments. Okay? So then, if you do it like that, you don't need then a dedicated emergency room anymore. And when they came to the hospital and presented this idea, they were pretty happy about that, because this was a really new idea that they haven't considered. Okay? And they were open for this one. Okay, so the objective is to minimize the break-in interval. So this is basically a min-max problem, which is also not that easy to algebraically formulate. It's of course an NP-hard problem, and of course we need a heuristic. We could have a construction heuristic. You know that from transportation. This is having a basic, feasible solution, but if you have more time, then you can also improve it. Okay, and for this we need a lower bound. Okay, so the lower bound lambda is the length of these intervals. Okay, this is the minimum length. So if it's 50 minutes, you would like to assign the surgery like that you have always 15 minutes in between. So every 15 minutes a surgery finishes. Okay, the formula is simply the occupation interval, E minus S, divided by the denominator. So the first one here is, so, but because you have slack time at the end, still it is possible to finish on time, because you plan with these duration variations. So you hedge in some sense you hedge against these uncertainties. Sure, yeah. Then of course you have to reschedule it in general. Yeah, that's absolutely. Sure. Yeah, definitely. It's just for planning purposes, so that if they come in, we have some possibilities. But you're absolutely right. If they sum up, then we have absolute different break-in point moments then at the end. Absolutely, yeah. Yeah, correct. Okay, so for the denominator, you have to differentiate between, we are not counting events, we are counting the intervals. Okay, so the first one here is the initialization, as the first interval, and then m minus 1, so we need always the gaps, okay, that we sum up only the intervals. Okay, and I think you know the difference between the set and the cardinality. Okay, so then the idea is to construct the surgery and assign the surgery so that these intervals are close to this lambda. Of course, if your lambda is 15 minutes, but or 2 hours, and your surgery, the minimum surgery duration is 2.5 hours, you cannot reach that. That's obviously, but as close as possible, that would be good. Okay, and I would like to show you the construction heuristic. So you have a fixed goal. So you start with to determine lambda and to set t to 1. Then determine completion times for unscheduled surgeries. Okay, so you have a list of surgeries that you have to assign. You determine all the completion times. Then you determine the maximum completion time for each operating room. Then identify the set of surgeries with minimum completion time. So you create, in some sense, a subset of surgeries, okay, where the completion times are less than or equal to the minimum of the maximum completion time. Okay, so this step basically filters out the surgeries that can be completed within the desired time frame. Then select the optimal surgery to schedule. So select the surgery that minimizes the difference between completion time and S and the product lambda times T here. Okay, so this ensures that the selected surgery fits into the interval, okay, and we maintain this even distribution, okay. Schedule the surgery, and if there's no other surgery left, then stop. Otherwise, start with the second step again. So this heuristic aims to evenly distribute surgeries across available slots, okay, by calculating this lambda and try to be as near as possible to this lambda so that we have an efficient scheduling process. Okay, and of course this is a pretty theoretical explanation. Let's start with an example, and we make some kind of social event now. I'm looking forward. So you have two operating rooms, both start at 8 a.m. You have two surgeries, two operating rooms, one that takes 2 hours, 4 hours. The third patient requires 3 hours and 4.5. You calculate all these things. You also calculated lambda, and now I would like to assign you two groups for the last 15 minutes so that you can discuss this heuristic, this fixed goal heuristic, and apply this one to this example. And I would like to assign you so that you don't know each other yet. So I think, can you come over here, please? Yeah, you. No, you, to the right. The girls can stay together, I would say. You can go to the girl behind. You with the, to the, that one. Maybe you can come over here. Yeah, you have to move, I'm sorry for that. Yeah, you can go to this guy, exactly. And you in the back, you can come over here. Yeah, you to that one. Okay, and I mix you guys, so you can come to him. Yeah, you. You have all white shirts. Sorry, this is really difficult. So you with the glasses at least are coming with the first row. Sorry for waking you up, but I thought social interaction is a fun thing to do. So, and okay, we need a, no, you know already. So you have to go to these guys, okay? Okay, so the official task is to use this heuristic. The unofficial task is to talk about your hobbies, favorite clubs, vacation destination, whatever, Simply exchange your names, that would also be great. So at the end of the day, I would like that you know each other so that you can help each other, okay? So this is the actual task. But for the next remaining, let's say 10 minutes, I would ask you to discuss the heuristic officially. Okay, have fun. guys, I hope you took it very seriously, your task, all right? Just last 5 minutes, I would like to explain that because the explanation was really complicated, but at the end, it's not really a fancy heuristic. The first step is simply to use the maximum completion times of the operating room. So for operating room is 12 p.m. And for the second one is operating room is 12:30. This is the first step you have to do. Then take the minimum of the maximal completion time. This is 12. So therefore, you can choose now to assign surgery 1, 2, and 3 because all of them are faster or as 12. Okay, so surgery with completion times that are less or equal to the minimum. You can choose, before 12. And now the last step is choose the one that is closest to our lambda, of 2 hours. By the way, the 2 hours here is not really realistically. If you have emergency and the emergency patient has to wait for 2 hours, that is might be too long, so in practice. But here for our purposes is 2 hours, so we would like to assign the surgery that is closest to this 2-hour slot. Okay, so if you determine this lambda times t minus the completion time minus s, you can see if you assign the first surgery, then you have a difference of 0, so yeah, this is it's not possible to get closer. If you have, if you assign the second surgery, then you would have a deviation of 2 hours, or if you choose the third surgery, then you have a deviation of 1 hour from our lambda. So therefore schedule the surgery 1 first. Then set t to 2 and start the entire process again. So this is basically it. It sounded fancy, but at the end it's pretty straightforward. Then we could have some kind of improvement heuristic. Taboo search, you already know that. And then they had some kind of computation results. So they had a lot of data, so 500 periods, 500 days of data distributed for the last 10 years. And then they determine different numbers, average runtime in seconds, maximum break-in intervals in minutes, and so on, so as before. And then that was the computational result. So the original schedule taken by the hospital, they had an average break-in interval, so the emergency patient had to wait on average 66 minutes for the surgery, and they only had 2 number of times the lower bound was reached, so the lambda was reached, only 2 times. When they scheduled that as before, then they only had 2 intervals that were exactly like the lambda. So if you use some kind of construction heuristic, then you can improve that. If you use the improvement heuristic, you can even improve it to almost half an hour waiting time for the emergency patient, and you have a much more number of times that the lower bound is reached. This lambda is reached, and the fixed goal values could decrease this. Here's the fixed goal. It could already decrease the interval significantly, but with the improvement you can go almost to half an hour. And they had also, this was for 6 operating rooms, and if you increase the operating rooms to 16, then you can see that the improvement effects are not that significant anymore. The more you have. And then you use some kind of simulation also, and the same as before. So if you consider the simulated average, then you can also maximize the interval. So we don't need any kind of improvement heuristic here. So it's enough if you use the construction heuristic, so the fixed goal heuristic already. And with this, I would like to thank you for your attention, and we finished this topic, and we'll start next week with the rostering planning. Thank you very much for your attention. See you next week. Bye.